Okay, let me unmuted, video sharing. All right, good to go. Okay, so as I was sitting here reminiscing about the last, 5-6 minutes before the break, I want to emphasize the point that I was not intentionally, I was intentionally belaboring the pictures showing the random intercepts and the residuals. Understanding those concepts, whether you understand the notation for it, whether you understand conceptually what's going on with it, is critically important to your understanding of everything else we're going to talk about here. So again, understanding what a random effect, what a random intercept actually represents as a deviation from some sort of a group-specific deviation from what was seen on average, and then understanding where that remaining residual variability comes from as deviations from a person's own group's mean is critically important. Okay? Because that terminology, again, is going to bleed through the remaining 3 hours we have here. So part 4 of 12 is talking about the intra-class correlation. So again, multi-level models, quote unquote, handle dependency. Where does that correlation go? Again, dependency is just a synonym for excess correlation. So where exactly does it go? Well, it goes into a new variance component. Okay. So what we're going to do is from our single level garden variety linear regression model, we're actually going to partition that single variance component into 2 variances. Remember, we have deviations of the group's mean from what's seen on average and deviations of people from their own group's mean. Again, level 1 within group differences. Those are our residuals. That's our residual variance. Level 2 between group differences is going to be captured by our random intercept collected across random intercept variance, tau squared UO. What you are going to see in the code and the output from the software is that once we include a random intercept in the model, our residual variance is going to decrease. Critically important is that we are not explaining variance. Okay, we're just partitioning it, moving it someplace else in the model, but that variance as a sum is still there. The only thing that explains or reduces variance components are the fixed effects from predictor variables. When we include a random effect in the model for the variance, we are not explaining or predicting anything. We are just partitioning variance out, identifying the excess correlation that needs to be accounted for. Okay, so again, the residual variance is going to be lower from your linear regression model to your multi-level model, but that is not something that you want to calculate R-squared on. So empty means random intercept model. Empty means just means unconditional or no predictors. So our empty single level model, which we saw earlier, is model 1 from the fixed effect example, just has a fixed intercept and a residual. Our empty multi-level model now has those intercept, that beta 0j, serving as a placeholder for something at level 2. Again, subscript I is for the person, j is for the group. Beta 0, j means we have an intercept specific to every single group. We also have a residual value specific to a person for the group that they're in. This placeholder beta now is going to be at level 2, with which we have our fixed intercept, which now is moving from beta to gamma. So gamma 0, 0 is going to be our fixed intercept plus our U value, U0, indicating our random intercept. It has a subscript J, meaning that every single group is going to have their own random intercept. We can substitute in gamma 0 plus UOJ into our level 1 equation to get our composite equation. Okay? So our residual value, again, person-specific deviation from the group's predicted outcome. Our random intercept is our group-specific deviation from the predicted intercept, fixed intercept. The fixed intercept is just the mean of the group means, given there are no predictors yet. It's unconditional. And in this, there's actually 3 parameters estimated. I start with this counting parameters because it's important for when we're conducting model comparisons. In the model for the means, we just have a fixed intercept. In the model for the variance, we have a residual variance and a random intercept variance. So again, this model notation is doing exactly what the pictures we saw before the break showed us. The way we quantify how much variability is at the group level is via the intraclass correlation. So again, whether you like words or equations, great. So we have our between group variance divided by between group plus within group variance, our total variance. Random intercept variance divided by random intercept variance plus residual variance, or in notation, we have this here, okay? Every time we create a level in a multi-level model, the levels are assumed to be fully uncorrelated with each other. So what that means is that if I add the random intercept variance to the residual variance, I get back something that represents the total variability or total variance in that outcome. We don't have to add 2 times the correlation or anything like that because there is no correlation. That correlation is 0 or assumed to be 0. Okay. So this is literally level 2 divided by total is one way to think about the ICC. So it's the proportion of total variability that's between groups. It can be considered the average correlation amongst people, but if you look at this equation, you realize immediately that it can't be negative because variance components, although mathematically can be negative in stats land, they can't be. So this is a correlation that is always going to be positive. So that average correlation kind of falls apart if somebody says, well, why can't it be negative? The answer is based on the equation. In any case, the reason we're defining the ICC is that proportion of total variability that's between people. It basically quantifies how badly we need to worry about that excess correlation. It defines our need for the multi-level model. So our intraclass correlation in terms of pictures, larger ICCs imply more between group variability. So again, that between group variability captured by our random intercepts are deviations of each group's mean from the fixed intercept. So again, there's a lot more variation between groups than there is within groups. So that's going to produce a larger ICC relative to something like this, which is going to produce a smaller ICC. There's less between group variability and more within group or residual variability. Okay. One of the questions that pops up a lot, and there's actually a lot of methods literature related to it, is can we ignore clustering? Do we need a multi-level model if our ICC is approximately 0? And my answer to that is unequivocally no. The reason that is that our unconditional ICC, which we saw in the previous 2 slides, are going to differ from our conditional ICC. Remember, predictor variables have fixed effects that explain variance. So if we include a bunch of predictor variables that are explaining level 1 residual variance only, what's the only thing that can happen to our ICC? We're decreasing the denominator, meaning our ICC is going up. So if somebody says, well, our ICC is approximately 0, the first question you should ask is, well, is it conditional or unconditional? Because again, including predictor variables is going to shift that ICC around. Okay. The other thing is if you're explaining residual variance, you're actually going to see an increase in random intercept variance. It has to do kind of with reliability. So your estimated random intercept variance is some function of true score plus error. For those of you that have reliability training kind of in the background or classical test theory stuff. If you only explain level 1 residual variance, you're going to see an increase in random intercept variance, which means you're going to get a negative R-squared value. We're going to see this in one of the examples we're coming up. That is normal. That is normal because of this equation. Okay. In any case, big picture of this slide, there is no non-ignorable ICC. Just use a multi-level model until the software blows up in your face. And it will, and we'll see that it has in our example going forward. Whether or not that intraclass correlation is statistically greater than 0, the way we test that is via model comparison. Okay. Model comparison is going to be based on our -2 log likelihood. Okay. In SAS and SPSS, it's given as our -2 log likelihood or -2 residual log likelihood if we're in REML, but it's given as log likelihood in both Stata and R, which means that if you're not using within software code to conduct this deviance difference test or likelihood ratio test for model comparison, you're going to have to multiply the log likelihood from Stata and R by -2. Once you have your -2 log likelihood, smaller is better. The question becomes, how much smaller can it be? I don't want to dive into estimation too heavily. But there are two estimation flavors that you're going to see in your software, at least for the mixed procedures. Maximum likelihood versus residual maximum likelihood. Residual factors out the fixed effects. And so what that means is, for model comparison purposes, if you're in residual maximum likelihood, you have to make sure that the same predictor variables are included in model 1 as the reference and model 2 as the comparison. The only thing you're changing is those variance components. Okay. So the way we calculate our likelihood ratio test is we actually calculate the difference in -2 log likelihoods from the first model and the second. We calculate the difference in the number of parameters. So we saw earlier from our empty model, we had a fixed intercept and a residual variance from our single level model. And then once we added a random intercept variance, now we had a fixed intercept, random intercept variance, and residual variance. So we had 3 parameters versus 2 for our comparison model. That difference in -2 log likelihoods follows a chi-square distribution. And that chi-square that difference then is going to be compared to a critical value from a chi-square distribution based on degrees of freedom, which is our difference in the number of parameters. Okay. You can do this in software directly. I also have an Excel spreadsheet for the example that will show this as well. A few musings. The first is, again, I don't want to dive into estimation too deeply, but the -2 log likelihood is actually summed across observations. So if you have missing data, if you include a new predictor and it has missing data, you're going to be excluding rows like we saw earlier, which means that when you're excluding rows, you're going to have less data to sum across, which means you're necessarily going to have a lower -2 log likelihood. That lower -2 log likelihood did not occur because your model fits better necessarily. At least some portion of that is due specifically to just having fewer observations to sum across. The other thing is, when you're adding parameters, -2 log likelihood has to come down. And so your model can either fit statistically better or not better. If you remove parameters, -2 log likelihood goes up, which means it can either fit statistically worse or not worse. We're going to do a lot of the model comparisons as needed going through here. The other thing that I see a lot is, we get a random intercept variance and it's a specific value, and people are like, what does that even mean? And so the way we quantify those random effect variances is actually to put them onto something tangible, like the scale of the actual outcome itself. Okay. For example, if the random effect variance was statistically significant via model comparison, we have to provide some context. Let's say the fixed intercept came back as 1.966. This is not an arbitrary number, with a significant random intercept variance of 0.0005. So this kind of small random intercept variance was deemed to be statistically significant. So the multi-level model fits better than the single level model. But what does this 0.005 actually indicate in terms of the outcome? The way we quantify that is by using something called a random effects confidence interval. Conceptually similar to the confidence intervals you would have calculated previously, fixed effect plus or minus 1.96 times the standard error. The difference is, this is not based on a sampling distribution. This confidence interval is actually based on your data itself. So the equation looks similar. We're going to take our fixed effect plus or minus 1.96 times the square root of the random effect variance, so the standard deviation of the random effect itself. Okay. Again, not a standard error, a standard deviation. So based on these data above, 95% random effects confidence interval is going to be 1.966 plus or minus 1.96 times the square root of 0.005. It gives us an interval that goes from 1.827 to 2.105, which means that our groups, again, this is a data thing, not a sampling distribution thing, an observed data thing. Our groups are predicted to have an average disability score of 1.966, with 95% of those groups having average disability scores between 1.8 and 2.1. So we've taken that random intercept variance, thinking back to the pictures where the group means are actually scattered around that fixed intercept. We're actually quantifying where 95% of those group means are. So we've taken this 0.005 and moved it onto our disability scale. Before we dive into the example, one thing I want to cover very quickly, again, I'm not here to scare you with this matrix algebra, is the model assumptions via matrices. This is going to be important when we come back to the software. So some of the terminology just has to be here, okay? So this is our composite multi-level model equation. This is it in a much tighter, more compact matrix form. Don't worry too much of this. If you hate matrix algebra, you know, I do too. It's fine. X is going to be our predictor variables. Beta is going to be our fixed effects. Z is going to be the variables that have random effects. U is the actual random effects, and E is our residuals. Okay. The question we're trying to answer here is, where exactly do these variances go? And the reason we have to show the matrices is because the label they put on the matrix of residual variances or random effect variances matter. So again, our conditionally normally distributed continuous outcome is assumed multivariate normally distributed with some predicted mean, and in our matrix that it actually has a constant variance and independence. So this I is giving us a diagonal matrix, so 0 on the off diagonals, which means we have the assumptions of independence. The residual variances are actually stored in what we're going to call the R matrix. R is for residual. So whenever you see a bold letter R, remember that that holds our residual variances. The random effect variances, the variances of our U's, are going to be stored in something called G. So G holds random effects, R holds residuals. So if we have one group with 4 persons, our R matrix is going to hold our residual values. Our residuals are assumed constant across all people. Again, homoskedasticity. And the off-diagonal elements are actually 0. So this is our independence assumption. G is just going to have a random intercept variance, which is a scalar at this point. Just going to have a random intercept variance. For analysis, it actually jams it back into something called V, and it looks like this. Again, because the residual variance and random effect variances are uncorrelated, we sum them to get the total variance in the outcome for each person, with the off-diagonal elements representing the random intercept variance. So all of that excess dependency, all of the reasons observations are correlated is due only to the random intercept variance. These off-diagonal elements, again, are quantifying and holding that excess correlation we needed to worry about. Okay. So that's it. Big picture of what I just covered there. Residual variances in R, random effect variances in G. Analysis is actually done on something called V, but we're not going to see that very much. Okay, example time. Let's go to the grand mean centering PDF. And I also, if you're following along here, you can open the grand mean centering Excel file as well. I noticed on the website, there's actually 2 of these Excel files. Choose the one that's dated 11/30. Okay. Okay. So I am going to open up the grand mean centering PDF. Everything we saw for the fixed effect is exactly the same. So data management, it's all the same. Description, it's all the same. Descriptive statistics, it's all the same. Again, I wanted these documents to be standalone, so there is redundancy within here. Okay, question 2A. Quantify and explaining between state differences and disability using grand mean centering. So the first thing we're going to do is we're actually going to center an age variable that we're going to use later. I'm realizing that this probably should have been included after because we're not quite to that point, but we're going to go ahead and center person or respondent level age at 65 as well. Okay. So grand mean centering. A value of 0 on age P65 equals 65 years of age. I do that in all 4 software programs. Okay. Unconditional model to estimate the ICC for disability. So again, here's our equation. At level 1, we have our placeholder intercept and our residual value. Placeholder is going to be at level 2. We have our fixed intercept, and then the deviation of each group's mean from that fixed intercept composite equation is here as well. Now that we're adding random effects, the code changes a little bit in all of the software programs. So for mixed, we have disability. There are no predictors here before the comma, so we're still dealing with an empty model. So this is, again, fixed effects Our random effects follow the double pipe. So we have two pipes, and then we're putting ST, which again was our state indicator, colon is going to say we want to identify observations taken from the same state. So that colon is indicating we want observations grouped by state. We've seen variance, we've seen REML, we've seen residual denominator degrees of freedom. Covariance unstructured is going to define our G matrix. So our random effect variances are going to be unstructured. Unstructured just means it's going to estimate every variance and covariance. At this point, we're only requesting one random intercept variance. So unstructured really doesn't matter. Our residuals are going to be assumed to be independent. So again, constant residual variance on the diagonals, zeros on the off diagonals. Again, no excess correlation after accounting for that random intercept. We're going to ask for information criterion, which is going to give us our -2 log likelihood value. The N50, you have to tell Stata how many observations are at level 2, which I think is odd. But in this case, there's 50 of them because there's 50 states. And the nice thing about Stata is it will calculate the ICC directly for you using eStat. SAS and SPSS will not. So for proc mixed here, we still have the only thing now that we're adding from the fixed effects model is our random statement. We're going to ask for a random intercept. It's going to be structured by state, and it's going to have an unstructured structure to the data. Again, every variance and covariance estimated. Same type of thing here in SPSS. We're adding a random statement. We're asking for the intercept. There's a vertical pipe, and then structuring by state. R, we're moving into lemur. So we have disability with a fixed intercept. So that 1 is a fixed intercept plus, and then in parentheses is where our random effects go. So 1 is asking for the fixed intercepts, and then the pipe structuring by state. We're going to ask for a summary that's going to provide us with the fixed effects, or in this case, fixed intercept and random intercept variance and residual variance. And then we can ask for the ICC directly. So Stata and R produce the ICC for us. SPSS and SAS do not, and we'll have to go ahead and calculate them. And I'll show you how we do that. So here is our disability outcome. Again, disability underscore cons is our fixed intercept. Our fixed intercept still 1.966. So on average, the groups have a mean disability score of 1.966. What we really care about when we're estimating the ICC is our random effects parameters. So variance of our constant, random intercept variance is 0.005. Now you can see where this kind of came from from our lecture slides. But 0.0047, residual variance at level 1 is 1.5263. We can calculate, again, this value of 0.0047, that's all fine and dandy. But the reality is, if we want to put it back on the scale of the disability, we use our 95% random effects confidence intervals. We do so. We've seen this interval previously. We talked about that. What we really care about here is our intra-class correlation. So again, random intercept variance divided by total variance. So 0.0047066 divided by the sum of 0.0047066 and 1.52. That gives us an ICC of 0.0031. We can multiply that by 100 to put it on the percent scale, but approximately 0.3% of the variance in disability scores is at the state level. If you are operating in SPSS or SAS, I have this Excel spreadsheet here where you can actually type in the residual variance and the random intercept variance, and it will calculate the ICC directly for you as a percent. Okay. So again, you can do it by hand with a calculator. That's great. You can create an Excel spreadsheet. You can use this one even better, but know that it won't output those data directly for you. So the question becomes, this is a really small ICC, not much of the variability and disabilities at the state level. Okay. The question is this 0.0031 statistically significant? The way we test that is via model comparison. So our log likelihood, as estimated by Stata, is negative 660,001.8. We multiply that by -2. We get our value of 1.320036. If I go to my Excel spreadsheet for likelihood ratio test, the previous fixed effect model 1 that didn't include that random effect variance had a negative 2 log likelihood of 132,000 and change. Unconditional MLM multi-level model that we just estimated was 132 and less change. Difference in parameters in the variance components is 1. So we had 1 residual variance estimated here. Here we had a residual variance and a random intercept variance. So degrees of freedom is 2 minus 1. Difference in the negative 2 log likelihoods is 517. 1 degree of freedom. P-value is very small. So even though that intraclass correlation is really small, we're finding that including the random intercept variance fits the data significantly statistically better. Okay. So what does the fixed intercept represent in this model? It's the average number of disabilities across all respondents. So the fixed intercept of 1.966. So for every model we've estimated in this example, I also provide interpretations of all fixed effects, just so you know. So again, you don't have to write frantically as we're going through. Okay, so we've quantified the amount of variability that is between states, and that's 0.3%. So that is model 1. Okay, the next thing we want to do. So again, because we have used a random intercept to quantify between group differences, we can now include state level things to explain those differences. Previously in the fixed effects model, we just saw that there were differences, we quantified the differences, and that was game over. But again, because we've moved that variance into a new variance component, into a between group random intercept variance component, we now have predictable control of it. We can take state level things and predict why some states had higher disability scores than others. So that's where we're going to go next, adding level 2 group level predictors. We talked a little bit about this earlier. If you have a group level predictor and it's missing for some groups, it literally is going to be missing for every single person within that group. They're going to be excluded. That's list-wise deletion. The methods literature has been pretty strong showing that list-wise deletion is a synonym for bias. Okay, so keep that in mind. Think through what your group, what predictive variables you're going to include in the model first. So let's consider unemployment as a level 2 predictor. Again, we're going to center it at 2%, which we had already done previously. So this SMUE2 for each group is going to be the state-specific centered unemployment at 2%. So a value of 0 on the new predictor equals 2%. At level 1, we still have that placeholder and the residual. And at level 2 now, we basically have our fixed intercept and our fixed effect for state mean unemployment centered at 2. So our fixed intercept now is the predicted disability score specifically for a state with 2% unemployment, right? When all predictors equal 0, that's what our intercept represents. The fixed effect of state mean unemployment represents the difference in average disability for groups that average 1% higher unemployment. The change in the outcome per 1 unit increase in unemployment. Having the fixed effect, fixed effects, I should say, are tested not via model comparison. They could be if you're using ML, but they will, because we're working in REML, we're going to get p-values for them. So one thing to think about here, at least the way I'm going to address this in this workshop, is every single predictor variable we add is going to have a p-value associated with its fixed effect. So we can look at the p-value to determine whether it is statistically significant, and we will do so. Most of you know now, I would assume that journals are really pushing for effect size metrics over and above, p-values. And the way we quantify effect size is via R-squared. There's now going to be adjectives in front of these R-squared, though, once we move into a multi-level model. So one of the adjectives is going to be pseudo. So pseudo R-squared. For those of you who are familiar with logistic regression, this is not pseudo R-squared from logistic regression. It's not Cox and Snell. It is not Nagel-Kirky. It's not any of the other ones that people have defined for logistic regression. In fact, those aren't R-squares in the traditional sense. They're actually reduction in the negative 2 log likelihoods. This pseudo R-square we're going to talk about here from the multi-level model is conceptually similar to a traditional regression type R-square value. It's called pseudo simply because we can get a pseudo R-square now for every variance component in our model. We've seen in the previous model, we estimated a residual variance and a random intercept variance, which means we can get a pseudo R-square for our random intercept variance, and we can have a pseudo R-square for our residual variance. The reason, though, it's called pseudo is because they shift around a lot. This is a little bit of a nightmare, particularly as correlation starts to get wrapped up within this, particularly for the random intercepts. What that means is pseudo R-square can take on negative values. That can be a little bit of a problem. It's more common with REML as they factor out the fixed effects. But if you're writing up the results of a multi-level model for publication, this is really, a negative pseudo R-square is really difficult to explain. And so my suggestion to you is if you end up with a negative pseudo R-square, undoubtedly that's associated with a predictor that is not statistically significant. You can just call that pseudo R-square 0. It explained no variance, and that's a cleaner way to get through, okay? Because if you're trying to explain to somebody that it increased variance, that'll make their heads explode, okay? The way we calculate pseudo R-squares is very similar to what we had done previously. We take our variance component before, we subtract it off the variance component, the lower variance component after including our predictor variable, and then divide it by where we started from. Okay. There were equations that I had shown earlier for that. The subscript for pseudo R-square matters as well. So again, because now we can have a pseudo R-square for the residual variance at level 1 and random intercept variance at level 2, we have to tell our readers which pseudo R-square we're actually specifying. The calculation for residual variance is going to be exactly the same. Notationally, though, you got to tell your readers which pseudo R-square we're speaking to. Again, given the difficulties of pseudo R-square, we actually have an alternative called total R-square, and this is what we had kind of seen earlier. Quantifies total variance explained across all levels, and it is interpreted exactly the same as R-square from linear regression. We're going to get our model predicted outcome from our fixed effects only. We're going to get the Pearson correlation between our predicted value and our observed outcome, and then we're going to square it. That's going to be R-square. That's what we're going to call total R-square. Okay. So again, anytime we're adding fixed effects, statistical significance is going to be determined using p-values and whatever alpha threshold you're using. Effect size can be defined using pseudo R-square for specific variance components or total R-square for the total variance in the outcome. I'm going to calculate both here. Okay. All right, we're going to go back to the grand mean centering PDF and to the Excel spreadsheet, and we're going to look specifically at models 2A and 2B. So if I scroll down, the first thing we're going to add is level 2 unemployment. We can see the equation that we had earlier, actually. We have a fixed effect for state mean unemployment. The only thing we're adding to the mix statement now is we're telling Stata we want a fixed effect that we're going to treat as continuous for state mean unemployment centered at 2. We're also going to, again, use the predict statement to ask for predicted values that we're going to call pred M2A. And then again, XB is going to tell it to only include predicted values based on the fixed effects only, X beta only, and then we're going to correlate that. In SAS, we're just going to throw SMUE2 after the equal sign on the model statement. Again, we're using out PM to get fixed effect only predicted values, and then we're going to go ahead and correlate them with the observed outcome. Same type of thing in SPSS. So again, with is telling SPSS that we're going to treat unemployment as continuous. We're going to include that on the fixed statement, and we're going to ask for pred M2A, which is going to be the predicted values based only on fixed effects, and then we're going to correlate. For the lemur package, we're now outside of the parentheses because we're dealing with fixed effects. So fixed intercept plus fixed effect for state mean unemployment centered at 2. R, super nice with this, we can actually get our R-squared directly. So we can take our predicted values. RE form equals NA is telling don't use the random effects when calculating the predicted values. We're going to take those predicted values called M2A, correlate it with disability, and then square it and multiply it by 100 to get our R-square. So scrolling down, again, we're adding fixed effects here. So really what we care about initially is whether it's statistically significant or not. You can see that the fixed effect for state mean unemployment is 0.083. That p-value is less than 0.05, again, not 0, so less than 0.05. That coefficient indicates that for every 1% higher unemployment in a given state, the average disability score increased by about 0.08 points, which again is statistically significant. Thinking through our pseudo R-square, level 2 variables, state level variables, explain state level variance components. So this state level unemployment should explain level 2 random intercept variance. The previous model that we saw, model 1, was had a random intercept variance of 0.004766. The new random intercept variance is 0.0031313. That is a 33.5% reduction. Okay, so just state level unemployment explained a third of the reasons why there were between state differences in disability scores. It sounds like a lot, right? A third. Wow, that's almost R-square Hall of Fame. The issue with that is that you have to take into account the intraclass correlation. Remember, only 0.3% of the variability in the outcome was at level 2, which means that 33% is 33% of a very small proportion of variability in the total outcome. And so the way we actually slap ourselves in the face with that piece of knowledge is by calculating total R-square. So the correlation between the predicted values and the observed disability scores is 0.0193. If we square that, unemployment has actually only explained 0.04% of all of the variance in disability. So we have 99.96% remaining. Oof is right. Okay. So again, SAS, SPSS, and Stata will require you to calculate some of this by hand. So I have our R-square here. So model 2A, again, residual variance, random intercept variance. I'm recalculating the ICC. Again, as we're explaining variance components, you can see this ICC is actually bouncing around. It's a third less than it was when we started. And it's a third less because we've explained away level 2 or between state differences that are quantified by that ICC. As we explain or reduce level 2 variance components, ICC is going to come down. As expected, we have not reduced any residual variance from the comparison model. Again, level 2 things explain level 2 random effect variances. We've explained 33.5% relative to that unconditional model. Our Pearson R is typed in, which calculates directly our total R-square as a percent, so 0.04%. So again, whether you're using R or any of the other software programs, you can either ask for it directly or you can use the Excel spreadsheet to get it. Interpretations of all fixed effects are provided. Let's go ahead and add in right to work. Right to work actually is a binary variable. You either are a right to work, live in a right to work state, or you do not. So we're just adding an additional level 2 fixed effect that is at the state level. We can see we're going to treat it as continuous in Stata. We're going to go ahead and throw it on the model statement in SAS after with, and on the fixed effect statement in SPSS, and then still outside of the parentheses in Lemur. Okay, asking for the exact same thing conceptually. Again, asking for those predicted outcomes, predicted disability based only on the fixed effects, correlating and squaring. So if we scroll down, we can see here now that we've added in state level right to work. Because right to work is binary, again, 1 versus 0, this is a t-test, conceptually similar to a t-test. So disability scores of people who live in right to work states on average were 0.00 5 units higher compared to people who live in non-right-to-work states. It's a very small effect. P-value is not statistically significant. We can do the exact same thing here, okay? We can go ahead, calculate random intercept variance before adding this one, random intercepts after. Note that the pseudo R-square is negative. So when you've added, so we're estimating in REML, which again, factors out fixed effects when calculating the log likelihood. That again is an issue related to this. But basically, the negative pseudo R-square is also associated with the fact that we've added something that really doesn't contribute to the overall model. And so again, if you're going to write this up, I would report the fixed effect, report the p-value, and then say it explains 0% of random intercept variance. Okay. Total R-square is still about the same, 0.04%. And so if I go to our Excel spreadsheet here, you can see I enter the variance components, calculates ICC for us. We've still explained no residual variance because again, these are right to work was level 2 things. And then I have the level, the pseudo R-square for each level by comparison. Okay. The other reason that it might have increased is likely because right to work state and state mean unemployment share some correlation. So now we have unique effects after controlling for right to work state or unemployment. Once we have unique effects only, the variance again will have increased because the amount of unique variance is less. That's another excuse for a negative pseudo R-square. Again, it's easier to just say it explains 0%. Interpretations are provided. Okay. How's everybody doing? That was 50 minutes straight. I know this is 4 hours. I don't want to kill it off with too much of a break, but I also understand that cognitive capacity is finite. At least for me, it is. If you're lucky enough to be able to be tortured cognitively, good for you. But what are you guys thinking about? I know there's 116 of you, and loudest voices get heard. You want to take a break or keep going? Got 1 vote for good to go, Matthew Stackhouse. Full steam ahead. All right. All right. Good enough. Let's do it. Let me get a drink first. Here, I'll mute it so you don't have to listen to me.